Hey there, here we go into an awesome video that will practice the washer method. And in this video, we're going to go over just setting up but not evaluating the integrals that will find volumes of solids of revolution. Let's dive. So the instructions say set up but do not evaluate the integral that will find the volume of the solid made by revolving the following bounded region about the x-axis. So the region is root x and x squared. And you're going to see that I'm going to use this region again and again. I love that region. I think it's a very simple one. It's easy to integrate if you needed to, but it's easy to set up too. So we got root x and x squared. So that's root x, and then x squared would kind of go up like this. So the question is, where do they intersect? We're going to need to know that shortly. Now, well, let's just go ahead and find that because we need to know the region eventually. So let's find where they intersect. So that would be root x set equal to x squared. I square both sides and I get x equals x to the fourth. Never divide both sides by x, right? We get 0 equals x to the fourth minus x. And so I'll get 0 equals x times x cubed minus 1. And so that is going to yield us our two solutions, x equals 0 and x equals 1 because 1 cubed minus 1 is 0. So that's actually the point 1, 1. And this is the point 0, 0. Okay, so now, do we need those values right now? Well, we're eventually going to need them, yes. But for right now, we're going to revolve about the x-axis and see that what we get is a washer situation. Why is that? Well, if you revolve this whole thing, like so, it almost looks like a flower petal, you're going to end up with a hole right in the middle. And you can see that hole caused by all this space right there. So the area of our region, which is this part, is not flush against the axis we're rotating, so we need a washer. So now, if you recall, we have pi times the big R squared, so the radius of the outermost edge, all the way measured to the axis of rotation, and then the radius from the inner edge to the axis of rotation. That's little r, this is big R. So we've got capital R squared minus little r squared, all of that, and in this case it's perpendicular to the x-axis, so it's going to be dx, evaluated from A to B. That's our general template. So let's just fill it in and we'll be rocking and rolling. Now you only have to set up and not evaluate it. So this is going to be pi times the integral from 0 to 1. What's big R? Let's determine that. Well, big R is going to be equal to that curve minus 0, right? This minus this. No matter where you go, that's the outer curve. So that's root x minus 0. Little r is going to be, well, this curve minus that curve, which is x squared minus 0. And I do the minus 0 just so you can see the process. So big R squared is going to be root x squared minus little r squared, x squared squared. I think it's so important to kind of write out your template like this each time, and then it kind of tells you where it is you need to go shopping for information. And that's it. That's your answer. All right, we're going to do a few more of these just so that you can get a practice of the concept. You can integrate that in your sleep. Now, I'm going to continue with the same exact bounded region. The reason being, it kind of gets you used to that same concept. So same instructions, but this time we're going about the y-axis. So we've got y equals square root of x, y equals root x. We already know that intersects at 1, 1 and 0, 0. We found that in the last problem. But here's the thing. We're rotating it about the y-axis. Okay, so now when we do that, we end up with something like this. And I'll just mirror the petal, a rough picture of it. Not perfect, that's for sure. And you end up with something revolved like that. So now because we're revolving it about the y-axis and our radius needs to be perpendicular to the axis we're rotating, our radii, little r here and big R there, needs to be this way. Oh, well, if you recall, that means that we're going to end up with a washer flattened out this way, just like we did when we had a disk flattened out that way. So that means we have dy. So now everything's in terms of y. No sweat, we got this. But that also means we need to solve each function in terms of y. So this would be y equals root x. Square both sides, you have y squared equals x. This would be y equals x squared. Root both sides and you get root y equals x. You only need the positive root y because it's only the positive side of x that we're taking. So this right here is root y and this right here is y squared, just to kind of keep it straight. Okay, so we're going to have the antiderivative, or the integral from a to b of pi, big R squared minus little r squared, dy. Just like we saw in the disks, the thickness is now this way. We got this. So what's big R? Let's find that. Big R is going to be the distance from the outermost edge to the axis of rotation. That's this minus that, or root y minus 0. And that's x equals 0 this time. And then little r is going to be y squared minus 0. Another way of knowing that it's in terms of y and why that makes sense is the output we're getting are x values. So we're basically saying an x value minus an x value by writing it in terms of y and getting out x's. So now we just plug it in. Now in this case, we're really integrating from bottom to top. Remember that. But this point is 1, 1. We knew it was x equals 1. When you plug in 1 into either of those functions, you get out y equals 1. This is 0, 0. So you're going from y equals 0 to y equals 1, stacking it vertically. Pi is on the outside. Big R is right here, root y squared, minus y squared squared. Done. Just make sure you got your dy, and you are donezo. All right. We got 2 more. Let's do this. I'm going to take you through a couple of different other scenarios, and then the exercises are full. There's an abundance of different variations. But for now, again, I keep the same region just to practice the idea. Same exact region. Should just graphed it out once instead of having to copy it each time. Root x and x squared, but this time we're revolving it about the line y equals 3. Well, that's interesting. Oh, that's way up here. You know what? I'm going to put it a little bit closer just so that we can show a little bit of rotation. So let's say that y equals 3 is like right there. Okay, so when you revolve that, you're going to get something roughly like that. It's not perfect to scale, obviously, but you're going to get this rotation happening here, and you see this gap happening right there. Now here's what's dangerous about this problem. Our axis of rotation is above the region, but as long as you keep in the forefront of your mind that you need to have positive radii, you'll be in good shape. So let's go to our template. We've got pi times the integral from a to b. Now we're going from left to right here because it's about y equals 3, so we're going to be perpendicular to that horizontal line. So that'll be vertical disks and washers, if you will. So it's going to be in terms of x. Now, what we have is big R squared minus little r squared dx. All right. And if you don't remember why that is, just draw on a disk. You'll see that this thickness is that way, so it's dx. All right. So now what I've got here is little r is that, big R is this. And yes, it matters. I would draw the radius to the original region so that you see what makes things positive. So to get a positive big R value, that's going to be from top minus bottom. You don't do curve minus line, because that would give you a lower y value minus a higher one, which would give you a negative r value. That's incorrect. Even though you square it and you get the same value, it's not correct conceptually, and you'll lose points in the A, B, or BC exam for that. So upper value minus lower to the outer edge, that's going to be y equals 3 minus x squared. Isn't that sweet? I think so. This is going to be y equals 3 minus this curve, which is root x. All right. Now we just plug it in, and we are into our, well, integration part, but we only have to set it up. We're going to integrate from 0 to 1 in terms of the x values. R is 3 minus x squared. That's capital R. That's squared. Minus little r squared. I think it's so important, as I've said before, to just define little r and big R, because then all you have to do is plug it into your template. Oh, it's beautiful. All right, one more. Do you have it in you? I know you do. I know you do. Let's go. Let's go. Here we go. Set up but do not evaluate the integral that will find the volume of the solid made by revolving the following bounded region about the line x equals 1. Same exact area, but this time we're revolving it about x equals 1, which, if you recall, is where these two curves intersect. So when we revolve that about that vertical line, we're going to be in terms of y. And the reason why we're going to be in terms of y, well, remember that our disks are going to now be this way, right? So it's like you got to say disk. Washer is now going to be that way, like so. And so what ends up happening is you get that really, really thin height, dy. So we got to solve each in terms of each in terms of y, which we've done previously. You square both sides. X equals y squared. You square both sides here, and you get root y equals x. Again, we only need the positive root y because we're just dealing with the positive side of x on x squared. Now, draw in your radii. So this distance here is going to be the little r. That's the distance between the innermost part and the axis of rotation. This distance here is capital R. That's the distance from the vertical line out to the outermost edge. And so now we know that our main template is pi from A to B, big R squared minus little r squared dy. And let's close this one out nicely. Pi times the integral from 0 to 1. That's y values. We're stacking from 0 to 1, but that's 1 where the region ends. And then big R, what's that going to be? Well, big R is got to be positive, so it's going to be right minus left. If you do left minus right, you get a negative number. We don't want a negative radius. So that's going to be x equals 1 minus whatever that curve is, which is y squared. That's the root x curve, y squared. So it's 1 minus y squared. Little r is going to be this curve minus that one. That's 1 minus root y. Nice. We're sure of that now, so you don't have to hold all this stuff in our head. We just plug it into our template. 1 minus y squared squared minus 1 minus root y. It's all about how you organize your information. Deal with the concept first, then plug everything in. And integrating this is a bear. So for right now, I just want you to get the concept down, and I want you to practice by doing this. Just kind of nail out the concept each time. That was fun. I can't wait to see in the exercise. We got a bunch of problems that'll go over every single kind of situation you could possibly imagine when it comes to volumes of solids or revolution. When to use disk, when to use washer. It's a good time. I'll see you there. Peace.